In this video, let's explore the angle between wavefronts and rays of light. The angle between these two. And why should we do that? Well, we will see in future videos, it'll be really important for us to be able to reconstruct wavefronts given the rays of light, or given the wavefronts, draw the rays of light. It'll be really easy to do that if we understand the relationship between their, the angle between them. And that's why we're exploring that. Now, before we start, let's quickly remind ourselves what wavefronts are. Well, I always like to go back and look at the animation representing Huygens picture. Wavefronts are basically a set of particles which are oscillating in sync with each other, which are in phase with each other. Over here, if you look at these ripples are what represent the wavefronts. Since these ripples are spherical, this is in 3 dimension, we say the wavefronts over here are spherical in nature. And why do we say that? Well, that's because if you look at a particular sphere, notice every single particle on that sphere will be oscillating in sync with each other. Look at that. They'll be oscillating in sync. And that's why we say that this sphere represents a wavefront. And so over here, every single sphere, which is centered at the source, will represent a wavefront. And what we want to do now is find the angle between the wavefronts and the rays of light, okay? So if I were to draw those wavefronts, those spherical wavefronts, here they are, what would be the angle between these wavefronts and the rays of light if I were to draw them? That's what we want to explore. Now, before I do that, can you pause the video and think about this from this image? If you were to draw rays of light, what would the angle be? All right, let's see. If you were to draw the rays, those rays of light would be emanating outwards from here, right? Let's draw them. All right, there, that's how it would look like. And notice, that means these rays of light would represent radii to these spheres, because these spheres have a center at the source, and these rays of light are also starting from the source, and therefore they are radius. They form the radius to the sphere. And what's the angle between the radius and the surface of a sphere? That's always 90 degrees. So the angle between wavefronts and the rays of light over here turns out to be 90 degrees. The question is, would it always be true? Well, let's see. Let's consider another wavefront. Let's consider plane wavefronts. To get plane wavefronts, we'll have to go far away. So let's do that. Let's go far away from this source. That's when we get plane wavefronts. Now notice we have plane wavefronts. Look at the direction of the rays of light. Now the rays of light are parallel to each other. If this was like very far away, they would be perfectly parallel. But more important, look at the angle between these. It's still 90 degrees. In fact, it turns out that this is a general case. Let me close this. It turns out that if you take any wavefront of any shape, and the ray of light at any point on that wavefront, they will always be 90 degrees. Always 90 degrees. Now I could have said that and just closed the video, but what's really interesting is why. Why should this be true? It's really interesting. Okay, so let me clarify with an example what I mean. So let's say I were to draw some, some random wavefront. Okay, let me make it. Okay, random wavefront that looks like this. Okay, so now if I were to ask you to draw the rays of light due to this wavefront, on this wavefront, the way we would draw this, if this wavefront was traveling to the right, I would say that over here, the direction should be like this. This is how it should be, perpendicular. Over here, it should be traveling this way. The ray of light should be this way. Over here, the ray of light should be this way. Always perpendicular, you get the point, right? It has to be. And my question to you is, why should this be true in general? I mean, for the sphere and the plane, we saw it made sense to us, but why is this in general? Again, can you pause the video and think a little bit about why should this be true? And I'll give you a clue. Think about what would have happened if the rays were not perpendicular. Something would break, okay? Something in physics would break, and I want you to think a little bit about this. All right, hopefully you have tried. So here's how I like to think about it. I know that every single particle on this wavefront is oscillating in sync with each other, right? That's the definition of wavefront. Another way to say that, which is going to be helpful to understand this, is that every single particle must have finished exactly the same number of oscillations. If this particle has finished 3.5 oscillation, all particles must have finished the same number of oscillations because they're always oscillating in sync. So now let's think about what would have happened if the rays were not perpendicular. So let's say that this ray over here was not perpendicular. Maybe it was, I don't know, maybe it was somewhat like this. What would happen in this case? Well, let me zoom in. Then the way I like to do this is I would say that this ray can now be divided into two components. Okay, so bear with me, it'll make sense why I'm doing this. It'll be two components. One component which is parallel to the wavefront. So let me use yellow to represent that. There'll be one component of a ray parallel to the wavefront, and there'll be another component which will be perpendicular to the wavefront. Okay? Now let's concentrate on the ray of light that is parallel to the wavefront. We agree that the ray represents the direction in which the wave is traveling, right? The direction in which the light is traveling. So since there is a parallel component, we are saying that there is some light traveling along the wavefront. And that poses a problem. Why? Because if there are two particles, if I consider two particles very close to each other, consider these two particles very close to each other, we are saying there's a wave traveling from here to here. If there was a wave traveling from here to here, then these particles could not be in sync. This particle would have started oscillating first, and then this particle would have started oscillating. That's what happens along the direction of a wave. I mean, if you look at a string, for example, if this wave is traveling this way, can these two particles ever be in sync with each other? No, because this would always have finished, this got hit by the wave first, so it would have finished oscillations, some oscillations more than this one. And similarly, because the wave is traveling parallel, this particle would have finished more oscillations compared to this one. There would be some particle over here which would have finished more oscillations compared to this one. And that breaks our idea of wavefronts, because we said in wavefronts, all particles must have finished exactly the same number of oscillations. And therefore, there can never ever be a component of the direction which is parallel to the wavefront. And so the only component of the direction that can be allowed is perpendicular. And that's the reason why the rays of light must always be perpendicular. And this is super useful, because if someone tells me that there are rays of light going this way, and they ask me what would the wavefront look like, I can tell now. If it's in 3 dimensions and you have parallel rays of light, I know the wavefronts need to be this way, because I know this will always be perpendicular. If someone tells me that the rays of light are like this and ask me what does the wavefront look like, I can try drawing that wavefront. I'll try drawing the wavefront in such a way that it will always be perpendicular to the direction of the wave, the rays of light.